Good morning. So today we will continue the discussion on planar graphs. And first of all, I will talk about a new concept called homeomorphic. So it is not isomorphic, but it is a new concept. And this concept will help us to understand what is Kuratowski's theorem about. This Kuratowski theorem is proven by this mathematician Kuratowski from Poland. Okay, he's a Polish mathematician in 1930. So this theorem checks if a graph is planar or not. It gives us a very strong condition so that we can check if a graph possesses a certain property, then it will be non-planar. Otherwise, it will be planar. So there is an if and only if condition. And then to understand this, we need to have the concept of homeomorphic. Okay, and after that, we will talk about Platonic solids. So let's start. Okay. Okay. So first of all, let me define an operation called subdivision. So a subdivision operation is operated on an edge. So there is an edge, let's call it U and V. If we add a vertex inside U and V, then it is called a subdivision. So we have U and then V, and then we add a vertex inside. Let's call it W. Okay, so this operation is called subdivision. So we are going to divide this edge, a single edge, into two edges, okay, like this. Is that okay? So in this direction, this is called subdivision. And then you can think about the reverse direction. The reverse direction is you have a certain vertex that is joining exactly two edges. So a vertex joining exactly two edges. We can remove this to make it beautiful, to make it disappear. So in this case, we call this operation a smoothing operation. Is that okay? So we make this smooth. Okay? Is that okay? Now notice that subdivision always find an edge and divide it into two by adding a point inside. You can add a point here or you can add a point here. Is that okay? But on the other hand, if you are doing smoothing, then you need to be careful. Because smoothing is a reverse operation of this subdivision. So the vertex that you want to remove, you want to smooth this out, it must be joining exactly two edges. Is that okay? So by smoothing, you join these two together. So I'll give you an example which is not smoothing. So for instance, suppose that we have a graph like this. Okay, and then you try to remove this vertex into something like this. Then this is not a smoothing operation. To see that, if it is a smoothing operation, to change this to this one, then you can reverse the direction. So to get this graph from this graph by doing subdivision. So you may try to subdivide this edge at a certain point, but this point is not on this line. Is that okay? So it is not the same as, so this one to this one is not a smoothing operation. Okay? Now, so we are ready to define what is the concept of homeomorphic. Okay. Okay. So this is a definition. If a graph G can be changed to another graph H by a series of subdivisions and smoothings then we say that these two graphs are homeomorphic. We say G and H are, this is a strange word, homeomorphic. So you see this word, there is morphic here. Morphic means shape. So it is, they are having, the shapes are related in some way. So I'll give you an example. So let's consider this graph G. So let's consider this graph G. So let's say G is like this. Let's consider this graph H. So H is like this. Is that okay? So if you look at this example, then G and H are actually homeomorphic. Now to change from G to H, then you can try to smooth this vertex, because this vertex is a degree 2 vertex. We can smooth this, and then we can also smooth this. So to make it a straight line. And after that, we add a vertex here, and then we add a vertex here by subdivision. So in that case, we get this graph H. So that means that G can be changed to H by using some subdivision and then some smoothing, or we don't care about the matter, the ordering of subdivision or smoothing. Maybe subdivision, smoothing, subdivision, smoothing. So that after some subdivisions and smoothings, we can get H. Then in that case, G and H are homeomorphic. If you understand what I'm talking about so far, could you please raise your hand? Okay. So here, G and H are homeomorphic. It also means that H and G are also homeomorphic. So you can actually change from H to G. Okay. So we can get G by, so we start with H, and then we can also get G in the reverse way. So whenever we are doing smoothing here, we are doing subdivision. Whenever we are doing subdivision here, we are doing smoothing in the reverse way. Is that okay? So whenever G can be changed to H, then the reverse is also true. We can change H to G. If you are okay with this, could you please raise your hand? Okay, now, good. So we just need this single concept of homeomorphic, and then we can define what is the Kuratowski theorem. So it says that. Okay. So this is the theorem, the Kuratowski theorem. Okay. The Kuratowski theorem says a graph G is non-planar if and only if, so this is if and only if G has a subgraph homeomorphic to K5 or K33. Oh, so that's it. The theorem is very, very simple. It says that, okay, so if a graph is non-planar, it must be true that in certain part of this graph, there is a subgraph. And this subgraph looks like a K5, or it looks like a K33. So what is meant by look like? So we define look like by homeomorphic. So if there is a part of the graph, inside the graph, we can find a part, a subgraph, that is homeomorphic to K5 or homeomorphic to K33, then this graph has to be non-planar. Okay, the reverse is also true. If it happens that, so whenever it is non-planar, it must contain a K5 or K33. On the other hand, if it contains a K5 or K33, then it must be non-planar. Is that okay? Okay. Now, so what is the meaning of homeomorphic? Okay. So the homeomorphic, it looks like we are just simply adding a vertex inside between the edge. Is that okay? So intuitively, so this is by intuition, it does not change the planarity of this graph. So if this graph is originally planar, I add a vertex there, then it is still planar. On the other hand, if a graph is not planar, then no matter how you add a vertex here, it cannot become planar. So this is the basic idea. But to prove this Kuratowski theorem, we need a vigorous proof. I don't know how to do that. Okay. But let's see some example of how to apply this Kuratowski theorem to show that the graph is not planar. Is that okay? Now remember, it makes use of this K5 and K33 as the foundation. So we have actually proven that K5 is not planar before using the Euler planar formula. We also use the same formula to prove that K33 is not planar. So these are the basis case of this Kuratowski theorem. Okay, so let's take a look of some example. So for instance, this is a graph K5. Let's start with a K5. This is a K5. Is that okay? So if I add things here, this is not planar. Is that okay? The reason is that originally there is no way that we can put this K5 onto a plane and then we add things to make things even more complicated. So it is still not possible to make this into a plane. Now, let us add a vertex here. Let us add some vertex here. So these are some subdivision operation. Is that okay? Now, adding these two vertices by our intuition is still cannot make this graph planar. Is that okay? But I don't know how to prove this. But by Kuratowski theorem, we know that this is still not planar. The reason is that we can find a subgraph inside this graph. This is the subgraph inside this graph, such that the subgraph is homeomorphic to K5. So if this is the case, then this is not planar. If you're okay with this, could you please raise your hand? Okay. Now let me give you another graph. So this is tricky. Okay. This looks like a K5, but it is not a K5. So I'm going to give you something called a Peterson graph. So let me draw this first. So we have 5 vertices outside, and then 5 vertices inside. So the middle 5 vertex forms a star. Looks like a star. The outer 5 vertex forms a pentagon. And then we join these two, we join these two, we join these two, we join these two, and we join these two. Is that okay? So this graph is called the Peterson graph. And in fact, this Peterson graph is not planar. It is non-planar. And then how we can show? How we can show? Can we use this Kuratowski theorem to show that it is not planar? Now, Kuratowski theorem is very, very strong. Whenever it is not planar, there must be a subgraph. There must be, if and only if, there must be a subgraph inside this homeomorphic to K5 or K33. So inside this, what do you think? Do you think we can find a K5 subgraph? Or do you think we should? So if I'm asking you to prove that this graph is not planar, then then what should we do? Should we find a K5 inside, or should we find a K33 inside? Do you think there is a K5 inside here? If you think there is a K5 inside here, could you please raise your hand? Okay. Do you think there is a K33 inside? If you think there is a K33 somehow inside here, could you please raise your hand? Okay. Now, there is some easy observation. Okay, so look at it. So whenever we do subdivision operations or smoothing operations, all the nodes that is having degree not equal to 2 does not change their degree. If a node has degree 3, then doing subdivision or smoothing, you cannot smooth this vertex, right? And then if you do subdivision, it doesn't change the degree of the vertex. So whenever a vertex has degree not equal to 2, then the degree does not change. Is that okay? So smoothing or subdivision does not change the degree of a vertex. Okay. But on the other hand, if it is degree 2, then it may be gone by doing smoothing. So this is the case. Now, so in this Peterson graph, if you take a look, then it is not easy to find, or it is not possible to find a K5. The reason is that all the vertices here, they have degree only 3. They are connected to only 1, 2, 3. 1, 2, 3. 3 edges only. But in K5, each vertex is connected to 4 edges. So degree is equal to 4. So no. So this is not possible to find a K5 inside. So instead, for this one, let's try to find a K33. Is that okay? So we try to find a K33, although it looks really like a K5, but we should find a K33 for this graph. Okay, so let's do this here. Okay, so everyone remembers the Peterson graph, so I'm going to change it now. So first of all, let us remove one vertex, and also because we need just to find a subgraph, so I can freely delete vertex or remove edges so that it is still containing a K33. So what I'm going to do is, let us remove one vertex. So let us remove this vertex. Okay, so I remove this vertex, so I remove all the edges joining to it. Is that okay? Is that okay? Now, if you look at this vertex, it is now a degree 2. Am I correct? So let us smooth it. Okay, we smooth it. Smooth. Okay? This is a vertex of degree 2. Is that okay? If I smooth it, then what will happen? Then these two will join together. Am I correct? Okay, so anyway, let's smooth it. So this becomes a single edge. Okay. And then there is also a vertex here. Is that okay? Which is also degree 2. Let us smooth it. Smooth. Okay. Okay. So how many vertices are left? So they are now. So we delete one vertex and smooth 3. So we have now only 6 vertices. So if there is a K33, then these are the 6 vertices in the K33. So let's check. Okay. So let's call it vertex A. Let's call it vertex 1. Let's call it vertex 2. Let's call it vertex 3. Is that okay? Let's call it vertex B, and let's call it vertex C. Is that okay? So I'm now changing the labels into A, B, C, and 1, 2, 3. Let me try to draw A, B, C on one side and 1, 2, 3 on the other side. So we have A, we have B, we have C, we have 1, we have 2, we have 3. Is that okay? So if you look at it, A is now joining to 1, A is now joining to 2, A is now joining to 3. And for B, B is now B is now joining to 2. Is that okay? You can see B is now joining to 3. And interestingly, B is now joining to 1. Is that okay? Because we have smoothed this vertex. So B is now actually joining to 1. Is that okay? And finally, if you look at C, C is joining to 1, C is joining to 2, C is joining to 3. C is joining to 1, C is joining to 2, C is joining to 3. And that's it. So what we have done is, from this Peterson graph, we have found a subgraph. So what is the subgraph? The subgraph is, I just remove this vertex, so take away this vertex. This is the subgraph. And this subgraph is homeomorphic to a K33, because we can use some subdivision operations or smoothing, in this case 3 smoothing operations, so that after the smoothing operations we get a K33. And in this case, by Kuratowski, then this Peterson graph is not planar. If you are okay with this, could you please raise your hand? Okay. Now, okay, I'll give you one more. This is also tricky. Okay, so I'll give you a graph. This is a K5, right? This is a K5, and it is not planar. Now, if I add a note here, so I add a note here, what will happen? Is it planar or is it not planar? So I add a note here, it means that this note joins this to this one, this to this one, this to this one, and this to this one. So there is no direct edge joining from this one to this one, and there is no direct edge joining from this one to this one. Is that okay? So this is the K5 at the beginning, but now I add the note here in the intersection here. If you think this is planar, could you please raise your hand? If you think this is not planar, could you please raise your hand? Eh? Nobody? Okay, 1 plus 1 is not equal to 2. Okay, so guess. Make a guess. Okay. If you think this is planar, could you please raise your hand? Okay. If you think this is not planar, could you please raise your hand? Okay. Now, good guess for not planar, but unfortunately wrong. Okay. So although it looks really like a K5, but then this is planar. Okay. Let's move this vertex out. So we start with the same 5 vertices. So let's move the colored vertex here outside. Okay. So this is actually joining this one to this one, this one to this one, this one to this one, and this one to this one. Is that okay? And what else? We should need this edge and this edge. Is that okay? And what else? We just need to draw this edge. If we can draw this edge without crossing any other edges, then it's okay. So this is it. Is that okay? So to prove a graph is planar is usually very simple. You find a way to draw it. Is that okay? So if you can draw it, then without any edge crossing, then it is planar. To prove a graph is not planar is difficult. But now we have this Kuratowski theorem. So if the graph is small enough, then we can ask our computer to check. Okay, usually we can ask our computer to check. Is that okay? Okay. Okay. So this is what I want to talk about, this Kuratowski theorem, and then in your assignment, this homework. So we will talk about this on Wednesday. So there should be some question about checking whether a graph is planar or not. Okay. So try your best to do that. Okay.